So what I'd like to talk about today is the concept of a physics quantity called a wave. And waves are basically all disturbances in some kind of medium that moves energy. That is the whole purpose of a wave, to move energy around. And motion of a wave is called an oscillation. And the shape, no better way to describe it than to say that it's just a wave shape. So this is what a wave looks like. It starts at some height, goes down, goes back up, goes down, and then back up. And it kind of repeats this shape. The shape is what we call the oscillation. There are some terminology, key phrases that we need to know. There's this undisturbed point, which is basically kind of like the midpoint of the wave, halfway between the top and bottom of it. We call this the equilibrium point. So that middle line is the equilibrium point for the wave. We also have this height over here. That's called the amplitude. That's how tall the wave is from this equilibrium point. It can be a positive amplitude, or we can go down to this negative point. It can be a negative amplitude. If we're going up to the positive part, that top part, that's called the peak of a wave, or the top of the wave. And this bottom piece, the lowest that the wave goes, we call that a trough. Finally, the last key piece of terminology we want to know is how long the wave is. That's going from the top of a wave down to the bottom and then back up to the top. That has a specific name. That's called the length of the wave. That's the wavelength. Lambda, the Greek letter lambda, represents wavelength. So using this, we can kind of start to understand and study waves in general. So waves happen largely due to stuff that we've studied already. We can understand them in terms of Newton's laws. So if I have a wave shape and I have some force that acts up, force of some action, then I can make something move up. But then every force has an equal and opposite force. So the force of reaction, if we remember Newton's third law. So that reaction is going to bring the force back down. And then it might overshoot, and the force will come back up. And this force can cause it to oscillate, to move up and down, to move back and forth. We've already studied a force like that. It's called the spring force. And that's equal to negative k times x. This is something called Hooke's law. Where Ff is the spring force. K is a constant that tells you the stiffness of the spring, or how hard it is to deform. You can think of the spring force as the force acting on a slinky, or something that kind of bounces up and down. And then x is going to be the distance you are from your equilibrium point. So either how stretched out your spring is or how compressed your spring is. Now to do this, to actually use a spring force to deform something, you need to apply a force to move an actual distance. We call this work. And so every spring that we have out there has the potential to do some work, to exert some energy. So we often describe springs in terms of how much potential energy they have. And we call this elastic potential energy, so the bounciness inside of an object. So the potential for doing work based on a spring is equal to 1/2 times k times x squared, where these k and this x are still the same as they are in Hooke's law. K is the stiffness, or how hard it is to deform something, and X is how far you stretch or compress your spring. We can actually understand this energy and understand these oscillations in terms of sound. So sound is one of the most common types of waves. And sound waves kind of let you hear the energy in an oscillation. Because we need to remember, oscillations are waves, and the purpose of a wave is to transport energy. So if you think about a guitar, and you pluck it, you pluck that string, and you're making it oscillate. A pluck equals an oscillation. If I want a high pitch, I need lots of oscillating. And if I want a low pitch, I want to minimize oscillations. And this concept of pitch has another name in terms of waves. We call this frequency. And we can quantify this frequency in a very specific way. So the frequency of a wave is equal to 1 divided by capital T, which represents the period of a wave. And that's how long it takes a wave to oscillate one cycle. So we can figure out what the units of this frequency are by plugging in units. So the units of F are going to be 1 divided by the units of period, which is a time. So that's 1 divided by seconds. If we give this another name, we call this a hertz. Hz stands for hertz. And that's the unit of frequency. Now the simplest example of oscillation actually has a name. We call it the SHO. The simple harmonic oscillator. And this is anything that oscillates according to Hooke's law. So any kind of object out there, it doesn't have to be a spring, anything that oscillates according to Hooke's law. Which we should remember, F equals negative K times X. So things that orbit according to this, that oscillate according to this, they fulfill some special conditions. So the period of a simple harmonic oscillator is always going to be based on the equation period equal to 2 pi times the square root of whatever mass is causing your oscillation divided by K, which is the stiffness of your spring or your object that's actually oscillating. So the size of your oscillator and the stiffness of the spring in your oscillator, the amount that it will deform and how easily it will deform, determines the period of your oscillation. So we can use this to figure out what the frequency of a simple harmonic oscillator is. All simple harmonic oscillators will have the same frequency, 1 divided by 2 pi times the square root of K divided by M. So this is the inverse of the period. So we can notice here that the period and the frequency of a simple harmonic oscillator only depend on 2 variables. They depend on a spring constant K and the mass M. So given those 2 numbers, I can figure out how fast something's going to oscillate. And these aren't the only equations for the simple harmonic oscillator. There's more. And we can base these on the general shape of a wave. So if I draw a wave as a function of time, so we'll call it wave x as a function of time, a simple harmonic oscillator is going to move like this. It's going to move in this very characteristic pattern, this wavy shape, if you will. Now this equation, the equation of this line, if we were to write it out, we can recognize from previous math courses, hopefully, this is a cosine wave, where the simple harmonic oscillator has the equation x times cosine of 2 times pi over t times little t. So here in this equation, I can describe the different aspects of this wave. The height of that in this equation is going to be x. That's the amplitude. So this number that's out front of your wave, that's the wave's amplitude. This 2 pi over t, 2 pi over the period, that we should recognize is the frequency, the angular frequency of your wave, and little t is going to be the actual time. Now I can use this, and I could use methods of calculus if we were in a calc-based physics class. We don't need to worry about that in here, but I can take the derivative of this equation, if you remember anything from calculus. If not, not a big deal. So if I take this derivative, I get the equation for velocity of time. It's going to be negative x times 2 times pi over the period times the sine of 2 pi divided by big T times little t. And then I can take the derivative of this to get an equation for the acceleration. If I do that, I get the new equation, negative x times 4 pi squared over t squared times cosine of 2 pi divided by big T times little t. And I can do a substitution here where the acceleration due to time is equal to negative x times k over m times cosine of 2 pi divided by t times little t. So this lets me calculate all these things for the simple harmonic oscillator. These general equations will work in any kind of simple harmonic problem that I might try to solve. It turns out that a lot of systems, a lot of things that happen in the world can be modeled, can be approximated as simple harmonic oscillators. And one of those such things is called the simple pendulum. So the simple pendulum we can describe as being a simple harmonic oscillator if it's not rotating through angles bigger than 15. So if your angle of rotation is smaller than 15. So first, let's remind ourselves what is a pendulum. This is a kind of a rope that you tie to something, and then you have a little mass at the end of it, and you pull it away from the vertical, some angle theta, and you just let it rock back and forth. So it's going to move to the left, and then it's going to move back to the right. And it's just going to oscillate. It's going to move back and forth. So this is basically a wave, and we can model this like a wave. It's repetitive motion. We have some length L for every pendulum, whatever length of our string is, and some mass that we hang off the end of it. And as long as theta, this angle that we pull it back, is less than about 15 degrees, we can treat this like a simple harmonic oscillator. And we can find the period. So the period of the simple pendulum is 2 pi times the square root of the length of the pendulum divided by g. So what we see here is the only important aspect of the simple harmonic oscillation for the period of a pendulum is the length. And we get to this by doing some derivations, and you can check your book for these. 2 pi times the square root of k over m, which was the equation for period of a simple harmonic oscillator. So that means that this is the same as this. These are giving the same quantity. They're two different ways to calculate it. So you can use that in a variety of problem-solving approaches. You'll see some of that in your practice problems. And finally, we have the energy of a simple harmonic oscillator. So we're going through and describing all the quantities that we've been studying, how to get force, how to get position, velocity, acceleration, and we'll finally wrap it up with finding some energy of a simple harmonic oscillator. Energy of a simple harmonic oscillator is going to be basically the same as the energy of a pendulum. Kinetic energy plus potential energy. Now the kinetic energy is 1/2 mass times velocity squared. The mass of your pendulum or simple harmonic oscillator object times its velocity, plus the potential energy. And now if you're oscillating, your potential energy isn't due to gravity, it's due to your spring or whatever springy kind of object you have in your oscillation, whatever's the wavy characteristic inside of your problem. So we want the potential energy due to a spring, the elastic potential energy that we found earlier. That was 1/2 times k times x squared. And this energy is going to stay constant inside of a system. So those are more or less all the quantities that you want to know for doing problems involving simple harmonic oscillators. But that's not all we want to know about waves. We want to get a little bit more general, so a little bit more details on waves. Let's review a little bit. We have a wave-like shape. Starts up, goes down, down, and just repeats this pattern over and over. The height of the wave above the equilibrium point, that was the amplitude. The distance of the wave, the length of it, from the peak down to the trough, back to the next peak, that was called the wavelength. And if we take this whole wave and we make it whole move forward, all of it as a system, that speed that travels at is called the wave velocity. And the wave velocity is intricately or intimately tied to the wavelength of the wave. So the velocity of the wave is equal to that wave's wavelength times its frequency. So how long the wave is times the pitch of the wave. Or sometimes it might be more convenient to find the velocity according to wavelength divided by the period. So sometimes you'll know frequency, sometimes you'll know period. You just use whichever equation is most useful. There's two different types of waves that we can study. There's a wave that goes up and down. So that's what I've been drawing. That's called a transverse wave. And again, that goes up and down. The other type of wave is kind of tricky to draw. So you have a wave that spreads out and then gets really compressed and then spreads out and then gets really compressed and then spreads out. So this wave is called a longitudinal wave. And this one goes side to side. If you can imagine smacking a slinky and seeing a little pulse go down that slinky, that's what this longitudinal wave looks like. And with waves, some of the useful things we can do with them is we can combine them. We give this another name. We sometimes call this superpositions of waves. And there's two different ways to combine. We can do constructive interference, so adding two waves together, and we can do destructive interference. And that's subtracting waves. Constructive, you add waves so that they're in phase. Destructive are out of phase. And we could draw pictures of what this looks like. So if I have two waves, we draw a wave that starts up high, goes down, goes back up high. And we'll draw another wave that's exactly the same. So if I want to draw the combination of those two waves, and this is constructive interference, these two waves, let's say they each have a height of 1. They're going to combine together and give me an equilibrium point that's up at 2. And then I add up every single piece of this wave at every single point. And I can see at the bottom, I have a negative 1 and a negative 1, so I'm going to have a negative 2. And then again, the top of the wave is going to go back up to 2. So my wave in constructive interference is going to get bigger. It's going to double in size. Conversely, if I have a wave that starts at 1 and goes down to negative 1 and has this nice little wave structure, and then I have another wave, but instead of starting at 1, I'm going to start this wave at negative 1. So I start at the bottom, I go up to the top, then I go back down to the bottom. If I look at this wave and how it adds together, I can see I'm adding 1 to negative 1 and negative 1 to 1. So at all these points, this wave is going to cancel itself out. So I'm just going to end up with a flat line. I'm going to end up with absolutely nothing. So this is how we combine waves. Now the last important point to talk about is how can I set up waves on top of a string. So we'll talk about waves on a string, like a guitar. So this is waves that won't actually be traveling. They have another name. We also call them standing waves. So this would be the most general name for a wave on a string, standing waves. Now, standing wave has two specific endpoints, has two distinct places where it starts and stops. So we have a starting point where we start our wave, and we have an ending wall where the wave hits. Now with a standing wave, I can start a wave at one endpoint of say a guitar. And the wave is going to travel up, and then it's going to strike our second endpoint. So that's not a complete wave. All I've managed to do is I've started at the equilibrium point, I've gone up to reach the top, and then I've gone back to the equilibrium point. If I wanted to complete this wave, I'd need to keep going down to the bottom and then get back up to the top. So this would be one full wavelength. But what's actually going to happen to this wave when it strikes this wall, this endpoint, it's going to get reflected back. So this wave is going to bounce back and go back to the starting point. If it continued forward, it would look something like this. So, how do we describe this waves, this type of wave? Well, we usually describe it in terms of the length of the string, the length that we can cover. So the length between these endpoints is going to be equal to, we'll call it L. And what I can see by looking at this little picture is that the total length that I have here on this string is equal to 1/2 of an entire wavelength. So let's look at that again. So I've drawn this wave. My wave starts at the endpoint, goes up, hits a peak, goes down, and hits a trough. That is not a full wavelength. I've got to go all the way down again and all the way back up to the point where I started. So this whole distance, that would be one wavelength. And I can see by looking at this that I've only covered half a wavelength, so my length is equal to 1/2 of a wavelength. And this has a very specific name for a standing wave. This is a special case of the standing wave. This is what we call the fundamental node, or fundamental frequency. So we use this word node, and what that means, that's a point where you're at equilibrium at an endpoint, a node. We have that on both ends. We have nodes. And the place where the wave is most spread out, that has another name. We call it the antinode. And this first case that I've drawn here, this is called the fundamental frequency. L equals 1/2 of lambda. So how does that represent a frequency? Well, we can actually do a little bit of algebra. So I can multiply both sides of this equation by 2 to get lambda by itself. So lambda is equal to 2 times L. But I also know that velocity is equal to lambda times frequency. So I can get frequency folded into here. If I do a little bit of algebra, I can replace my lambda with f. So if I see what lambda is equal to v divided by frequency. That's by doing algebra on this equation. Then I can plug this in for my wavelength. So I see that 2L is now equal to v divided by f. So if I want the fundamental frequency in terms of actual frequency instead of doing it in terms of wavelength, I can solve this equation algebraically for f. So you should be able to do the algebra for that to see that f is equal to v over 2 times L. And this is what we call the fundamental frequency. It's the very first frequency I can play on this string. But there are other strings, other frequencies that I can play. Let's say I take this string and I pluck it so that it moves a little bit faster. I have to set it up if I want an actual frequency that I can hear so that there's some multiple of some wavelength on here. So I can go up and back down. That's my fundamental frequency. But if I pluck this string harder, I can get more waves on this string. So instead of getting just one wave, I can half of a wave, rather, I can get a full wave. So my next frequency, lambda 2, is equal to L. If I get a full wavelength on this string by plucking the string harder. We give this a name. Instead of the fundamental frequency, we call this the first overtone. We can again do our replacements using the equation v equals lambda f, which is always going to be true. Good general equation. I solve this for lambda and I plug it in to find that the frequency of the first overtone is equal to v over L. And we label this with the number 2. So the first overtone is the second frequency. And so on and so forth. I can get integer multiples of all the frequencies that I could put onto a string. So that's more or less waves in a nutshell.